All right. So RaptorJIT, a fast dynamic systems programming language. So first off, hi, I'm Max. I'm an open source systems hacker. I'm currently dabbling in high performance networking applications. And I suppose I should start with a quick rundown of Lua, just in case you don't know it. Lua is a simple, minimalistic, high-level language. It has like a schemish semantics and a Pascal-esque syntax. It has first-class functions, multiple return values, prototype-based object orientation, and it's surprisingly flexible. And its central data structure is the table, which is a hybrid between a hash map and a sparse array. And the canonical implementation of Lua is called POC-Lua, which is a simple embeddable interpreter intended to be embedded in C and C++ applications, among others. So here's an extended hello world to get you kind of familiar with the language. I'm not going to explain anything about it. I'm just going to let you stare at it a little bit and hope that's somewhat obvious. So LuaJIT is an alternative implementation of Lua. It implements a dialect of Lua 5.1.5-ish. Plus some extra goodies. That's why I'm saying it's a dialect, not just an older version. As its name suggests, it comes with a just-in-time compiler. And that compiler is really, really impressive and achieves performance competitive with C. It's also a really good language for expressing programs that are close to the metal, thanks to its built-in language support for accessing and operating on C data. And that I think personally that LuaJIT is a good systems language. Systems language here, I mean that it's a good language to replace C. Like an application that you would have previously written in C, you could also write in LuaJIT, and you would get very far with that. So here's an example of some LuaJIT code showing off its ability to poke at low-level data. So you can see here that the language has built-in primitives for expressing C data, such as C structs, and you can access that data and the fields as if they were native Lua objects. To illustrate that, for instance, if P here was instead a Lua table with containing a string or containing a C array and a Lua number, the code here wouldn't change at all. You could still access it the same way, and you could still copy to the C array contained in the Lua table. So, RaptorJIT is a fork of LuaJIT, and its goal is to be a really good systems programming language. With RaptorJIT, we want to do a couple of things. First, we want to simplify the implementation and improve maintainability. We also want to improve the compiler for heavy-duty server applications specifically. So we have a very narrow use case. We want to write systems applications, like we're systems hackers, and we want to create a systems language. And we have a more narrow set of, I guess, optimization targets. And we think that we can improve the compiler even more by targeting this narrowed use case. Especially, we want to eliminate performance pitfalls, meaning small changes that have big impact in performance, and as well as unexpected JIT behavior. So we want to make it more easy to understand the JIT compiler and to use it. And under the bottom line, we want to provide more reliable performance. So right now, LuaJIT performance is great. We just want to make it more reliable, and maybe even better in some cases. Right, RaptorJIT also adds new features. Among those is a low overhead profiler and a matching introspection tools for that data. And hopefully there are many more features to come. And that's where you come in, I guess. So, in order to simplify and maintain the code, we are doing, oops, sorry. In order to simplify and maintain the code, we are doing a big spring clean. So here's this pull request titled, Big Bang, remove all the features that I can live without. And yeah, it says merged. That's the purple icon on the left there. It removed support for all architectures except x86-64 because at the moment that's the only thing we care about and it's enough work maintaining one architecture. It removed Windows support and it removed LuaJIT's 32-bit heap mode. And this allowed us to get rid of a lot of if-defs. We're trying to get rid of all if-defs because we don't like if-defs. And that resulted in a total code reduction of roughly 50%, which I think is a big win. The LuaJIT interpreter used to be handwritten assembly duplicated for each specific architecture. And we have almost completed rewriting that virtual machine interpreter in C and hope that that will make it easier to port and change the language implementation, that is. And the rationale behind this change is that we spend most of our runtime in compiled code, meaning in traces, in compiled traces. So for our use cases, high-performance networking, spending any significant time in interpreted code is out of the question anyway, because that would be way too slow. So for us, an interpreter that's fast doesn't really do anything. We really don't need an interpreter that's like heavily optimized. So our idea is that, look, we're going to make it easier to maintain, and we're going to skip the optimizations that we don't benefit from. And instead, we want to make it more easier for your code to stay compiled and not fall back into the interpreter. So we're also looking to remove complex optimizations that don't carry their own weight anymore. So here we removed a special case fast pass for string interning. And on the next slide here, I'm paraphrasing from the pull request, which somewhat reads, this fast pass, in air quotes, was bad because it was a tricky custom memcompare routine that needs to be maintained. It turned out to be slower than the stock memcompare on modern x86, which was the slow path. And it led to confusing performance behavior where unrelated memory allocation could bias often used buffer to the fast pass, again, the fast pass, and impact overall performance. So in the description, Luke concludes that the fast pass code was written 10 years ago and a lot has happened since then. And he goes on into how the CPU architecture, the operating system, that is Linux in our case, and even compilers like GCC had really evolved in that time, and goes on to say that I think the optimization had simply bit rotted. So what I want to stress here is 5? Okay. What I want to stress here is that this is not to bash this individual optimization or anything. It's just to say that if you have optimizations that are kind of smart and try to outperform certain components in your system, you have to account for the cost of maintaining them and the work of continuously verifying that they still actually work and still actually make your program faster, or just that weight. Okay, so I'm running a little bit out of time here. Right, so RaptorJIT wants to improve the JIT compiler. To understand the setting here, I guess I should explain that LuaJIT acts as a drop-in replacement for PUC-Lua. So it has a really fast JIT compiler, and it also has a really fast interpreter. So if the JIT compiler for some reason fails to compile a code path, it will drop into an interpreter that is still many times faster than the default Lua implementation, canonical Lua implementation. So in any case, if you have a Lua program that you use with PUC-Lua, you're going to have big performance improvements if you run it with LuaJIT, and so you're going to be happy. And we think that we can do better for a narrowed set of use cases with RaptorJIT. So to summarize here, the LuaJIT is for existing PUC-Lua code bases, and RaptorJIT is for new Lua applications written with a just-in-time compiler in mind. So in case you don't know how a tracing just-in-time compiler works, I will give you a super reduced explanation. A tracing JIT interprets code. When it hits a branch, it checks if it's hot or not. If it's not hot, it increments a hot count for that branch and continues interpretation. However, when the branch is hot, it starts recording a trace and then again continuous interpretation after recording a trace. And the next time it will hit a branch, which is not shown here because it's very simplified, eventually instead of hitting hot branches, you would start hitting executing traces of hot code. So with RaptorJIT, instead of treating the compiler like a special source that you throw into your Lua programs to make them magically faster, we want to foster a culture of understanding the JIT compiler. And with that understanding, we want to formulate design goals and implement them. And this should, in turn, again, make the JIT compiler easier to understand and, most importantly, easier to leverage. And the issue referred below here talks about avoiding high-impact medium generality optimizations. I touched on this before. So a high-impact medium generality optimization is, we call problems this term if they have the following behavior. So if you make a small change to your program and you get a big change to performance, that's what we call a high-impact medium generality optimization, because it's not general enough for you to freely make changes to your program that are like relevant in scale and scope, but it's high impact because you get a big hit if you fall off that optimized path, and that is how we want to. That is why we want to avoid unreliable compiler behavior, where small changes to your program cause big changes to performance. So LuaJIT aggressively blacklists code paths. It fails to compile. That favors the small, short-running programs. Our programs, the programs that we target, are all long-running. So just as a policy change, we spend way more time trying to find good traces, and we're good with that. We just want to make sure that we find the best traces for the program because we know that it's going to run for a long time. Yeah, as a first step in that direction, we updated the just-in-time compiler's heuristics for trace selection to match our target workloads. And yeah, not going to go much into that. On another note, LuaJIT doesn't actually consider the time domain when selecting traces. So a branch could become hot because it was executed for the 100th time after an hour of runtime. So the hotness is not actually frequency, but rather this abstract idea of some counter that at some point overflows. And I think that's really unintuitive behavior. I think that maybe RaptorJIT should consider the time domain and only compile code which is actually executed frequently. We did some experience with that. The results so far were positive, but that's just to show you the kind of hacking that we're doing on that fork. Right, we also added new features. We added a low overhead profiler. The intention is to have that profiler always turned on. It will always collect profiling data, even in your production applications, which you can then grab while it's running and display in this front end that we wrote to find which traces take the most time and what's the problem and see how they got created. This is to show that the tool that we wrote is a very visual tool. So this is a dependency graph of the immediate representation instructions, where you can see, this is the loop body and this is the head that's executed before entering the loop. Yeah, there's lots of experimentation going on. We've experimented with a trace barrier primitive that kind of like stops traces from going over that line of code and forces a new trace to be created, if at all. We like that one. We experimented with a JIT unlikely primitive, which too long to explain now. We didn't like it. And one thing I guess I want to touch on is that this JIT seal primitive, what this would basically allow you to do is declare or constify a table at runtime. And that would kind of give the compiler a superpower where it could treat tables created after configuration changes as constant and optimized based on those contents.
Just a few minutes left, so if you want to take some questions.
All right. Yeah. Yeah, I guess this one's important. I just have to mention it like in a minute. This is something that Vela has apparently already implemented and something we're really interested in because it removes another high-impact medium generality optimization. I guess check out the slides if you want to know more about that. Right, there's in general to JIT compilers, there's new literature, new science happening that really fixes some basic things. We could implement those things, and we're open to experimenting with that. And yeah, one of my personal goals would be to have safe foreign function memory access, where because all the information for foreign types, meaning C data, low-level data, we have all the type information for that available at runtime. So there's like nothing that really stands in between us making that type safe. And the compiler is really good at optimizing these checks, so that's something that I would like to do. Right. So thank you for your attention. Please get involved. We are on GitHub. And yeah, I would.
The next speaker can set up, and meanwhile you can.
Sorry. Yeah, I would be pleased if I got some of you interested in this project also, if you like into JIT hacking. I think this is a cool place to start. And yeah, if you have any questions, please. Yes?
Yeah.
No, I don't think so. I mean, maybe some bug fixes, but I'm not aware. Yeah. I mean, we have a very specific goal, and we are willing to separate and split. Like we want to cooperate with the other forks and exchange ideas, but we're really open to just like going wild on it. Anybody else? Yes.
Did you find any inspiration in LuaVela Forking LuaJIT, which was released just a couple of years ago?
Yeah, I think so. So when I started working with the RaptorJIT project, I actually wasn't aware of LuaVela, but I just recently reread some of the presentations and slides, and to me it seems that they're very similar in spirit, and they have some very specific features that they both want the same thing. And I hope that in the future there will be like a strong collaboration between these two projects, because some things that we want are already implemented in LuaVela, and maybe the other way around even. I think that LuaVela wants, for example, to have also try out the C interpreter, stuff like that, yeah. Anyone else? All right, thank you very much.
Thanks, Mark. Leave the microphone.
Yes.
Yeah. Okay, please.